Welcome back, everybody, and good morning, or rather, it's good afternoon with you guys, and it's early in the morning here. So this week, we have to catch up a little bit with what we missed last week, and I've updated the README file here with the further plans. So last week we did not have, or rather, I did not have the possibility to teach, mainly because I had a small problem with the definition of an outline of Project 2. So the kind of aim today is more to discuss this Project 2 and start the discussion of convolutional neural networks. Now, the video and the handwritten notes and so on, they will actually be uploaded at the GitHub address here. And if we go back to the kind of original plan, which we have, there is more material. So if you click on this link here and you scroll down, you will see that we actually planned a little bit more than what we have done. And there is also a set of slides on differential equations with neural networks, which we didn't have time to cover properly. So today, I'm going to start with this topic here, discussion of Project 2 and the start on the convolutional neural networks. And this is something which will keep us busy also next week. So we are delayed a little bit. So I was planning to have this on the 14th. And today we actually the 21st. So it means that we will also keep going with convolutional neural networks next week as well. And if we get into it, we will start with recurrent neural networks. And then we're also going to look at other deep learning methods like autoencoders, variational autoencoders, and if we get time before the break at Easter, we may look at the generalized adversarial networks. So this is roughly the plan before Anders Kvellestad takes over. And he will focus more on Gaussian processes and Bayesian neural networks and Bayesian machine learning, so which is more going to be his topic. And that's actually a very, very interesting topic, perhaps even more interesting than what we have done here, which is more the basic foundation for machine learning methods. So what I want to do now, unless you have any questions and things you would like to ask about before we go into the practicalities of the day, I just wanted to give you a quick outline of what we are planning today. So this would be the plans for today and also for next week. So the topic is about convolutional neural networks. And the plan is to first discuss a little bit about project number 2 and possible paths for that one. And then, as you can see here, there are some reading recommendations, and convolutional neural networks are very well discussed in Goodfellow's textbook. And this is a textbook which you can find fully online, chapter by chapter. And chapter 9 is the essential one for convolutional neural networks. It contains also very good discussions on chapters 11 and 12 on practicalities and different applications of normal feed-forward neural network, convolutional neural network, and recurrent neural networks. So the recurrent ones, which we will discuss a little bit later, in the beginning of March, is covered by chapter 10 in this textbook. There's also very much a hands-on chapter on implementation of CNNs in Aurélien Géron's textbook in chapter 13. And then there are tons of videos online if you want to look at them. Now, what I want to discuss with you now, and this is something which we can also iterate upon. So that means that if there are things which I have forgotten or things which you would like to have in Project 2, I mean, feel free to send feedback. So what I'm presenting here is just a suggestion from my side, and hopefully this can overlap with the research topics which many of you are dealing with. And as usual, we want to have lots of flexibility. So I'm actually proposing several paths here. And you should feel free to choose the one which is closest to your area of research and obviously your own scientific interests. So there's one path which I just labeled the computational path. And in that case, you could actually write your own code for a feed-forward neural network. as we have been discussing in the lectures. And I sent you also this code template, which is object-oriented, which contains a lot of the functionality, which you also discussed in project 1 with, for instance, gradient methods and stochastic gradient methods. So this will be more a computational path, and you could extend that to, say, recurrent neural networks. You can compare that with TensorFlow, and in order to make life easier, I would normally always recommend to use the API called Keras, which is an API to TensorFlow, which makes life much, much easier. Alternatively, if you're more familiar with PyTorch as a programming environment based on Python, so both TensorFlow and PyTorch are just Python-like programming environments where they have added a lot of functionality tailored to machine learning problems. So this would be a more computational path. And if that is something which appeals to you, feel free to follow that up. There are lots of things you can do there. And so just let me know which path is the more interesting one. Then there is one which I call the differential equation path. And it's a little bit similar to the partial differential equation path, which is number 4 here. And I'm going to detail a little bit about this path here. And here you can use the code you have written for neural networks. So you could actually interface this path 2 with path 1. So instead of you selecting a data set from public websites like Kaggle or the University of California at Irvine, which has a huge repository of machine learning data, you could then actually use your code to solve differential equations. And these codes can actually be extended upon if you want to. So everything you see here are just suggestions from my side. And you should feel free in a way to find the path which aligns best with your own research. So this is one type of course where we actually have this possibility to align what we are doing with own scientific interests. And I think that's the most beneficial for all of you, because the just doing exercises in a regular course is something which doesn't always overlap well with the scientific research which we are doing. So this second path, you could then just take the code you have developed. Alternatively, you could actually use the functionality of, let's say, TensorFlow, PyTorch, and other similar libraries. So you could extend this part here to actually look at the implementation of recurrent neural networks, which we will discuss a little bit later, and eventually also autoencoders. Autoencoders is just another way, if you want to think in more overarching terms. Autoencoders is a way to actually deal with dimensionality reductions. And all of these can be expanded into one large project. What I will be discussing in the lectures is actually how we can use neural networks that are trained to solve supervised learning tasks. You can also dive into physics-informed machine learning, which is a very hot research topic. Path 3 is more what I call the application part. And here you can use these relevant methods, which we have been discussing, say neural networks, convolution neural networks, etc., for image classification. And then you would apply these to data sets which are relevant for your own research. So in a certain sense, this path 3 is one which is totally open for you to define what you want to put into it. So if you want to apply convolution neural networks in connection with, let's say, you have a PhD project which is more tailored to classification of images, then this would just be one typical application of, or one typical path for project number 2 here. And then I also propose a partial differential equation path, because I know that some of you are actually dealing with the solution of partial differential equations. And I know that some of you are dealing with the solutions of Navier-Stokes equations. And for studies of Navier-Stokes equations, there is a lot of scientific activity going on applying neural networks or deep learning methods to the solution of differential equations. So if none of this is something which matches your interest, you can actually take data set. So you can propose own data set, or you have these popular data sets like the one which you find in Kaggle, the University of California, Irvine. Here, for the differential equation problems, you can obviously define your own data sets. And this is what I'm describing below here, how you can define your own data sets. Obviously, if you can, you should try to link the data sets with existing research and analysis, scientific articles which are linked up with the analysis of these data. This is in case there are publications. I mean, that's always useful. And clearly, as before, critical assessment of the methods with data perspectives and recommendations and so on and so on. By the way, before I move on, you will find, if you go back to this general link which we have here, this link which you see here, and you go into that one and you scroll down here, you will find the different variants of the project, either as a PDF file, a LaTeX file, a Jupyter notebook, the format which you wish to use with. So I put a tentative deadline on May 31. The same applies to the project number 3, but we are, as always, we are pretty flexible as long as we can grade and submit the grades by roughly the middle of June. That's the kind of hard deadline which we would have. So again, we are pretty flexible with that. You will also find the same files if you go into this doc folder and you click on projects, and then there you will find in 2022, you will find the same files for project 2. Okay, so that was just a kind of small digression. So what I wanted to do now is the type of problems which would link up with path number 2, but can also be connected with path 1. So let me just quickly remind you of path 1 and path 2. So path 1 is you writing a code for neural networks, for instance, and then you could apply that directly into path 2 as a data for the data set. Alternatively, you just stay with path 1 and use a data set of your own choice. So what I'm going to detail now is actually the data set which we can set up here and how we can use that in neural networks to make predictions. So let's look at that. So some of you may have encountered something which is called the Lorentz attractor model, which is a popular set of coupled differential equations for X, Y, and Z. And this is a model which has been studied since the beginning of the 60s in the last century, in the field of chaos in differential equations. And it's a very popular model. And we are going to use this model here to generate the data, which then can be fed into a neural network. Alternatively, if you don't like this model, you can provide another model. So down in the slides here, you will find another model, which could then be used as an input to a neural network. So what we are going to use now is to use the solution of a differential equation to define the inputs and the outputs to a neural network. And then we're going to train a neural network and see if that can make a prediction on data which were not included in the training, and see how well it does in predicting the solutions compared with a reliable numerical solution from, let's say, a Runge-Kutta method to fourth order, which is a popular method for solving differential equations like these. So feel free to interject with questions. So this is the model which we are going to use to generate the data. And we're going to solve a differential equation with a Runge-Kutta method to fourth order. And these parameters, sigma, rho, and beta, they're just parameters which we have given fixed values. And what I'm using in the code, which you will see below here, is simply to use the ordinary differential equation library, which follows NumPy and SciPy. And I just fixed delta t, this step size in the differential equation solver, to 10 to the minus 2. And I put a final time equal to 8 here. That's the final simulation time, from 0 to 8. So this is a dimensionless equation, by the way. So what I'm doing then is to define 100 random initial values. And they produce inputs and outputs for neural network. And the inputs are given by the value of the array X, which contains X, Y, Z as a function of time for the time step X of t. And then the output is the other time step, one step ahead. So let me just quickly remind you of what we are talking about when it comes to differential equations here. So I'm just going to bring up the whiteboard quickly, just as a small intermezzo here, just to show you what I'm actually meaning with this type of calculations. So we have a set of differential equations which we want to solve. And these differential equations are given in a more generic form. So we would have a differential equation where we have a function we want to solve, a dy dt. So let me rather write dx, because that's what I use as a kind of a generic variable. So in the project description, x is now going to be a vector which contains x, y, and z. But now we're just leaving this as a general quantity. And this is now given by some function, x and t. We're assuming that it doesn't have a dependence on the derivative. But so this function here depends on x and t. And typically when we discretize, then x goes over to an x of I, and same with t, which goes over to a t of I. And I'm keeping the same naming for the variables. If you wish to be picky, you should in principle set different names for the variables. And typically this t is then defined for a domain from t0, t1, up to some t of n. So we have n plus 1 points. So that means that this I goes from 0, 1, up to n, in total n minus 1. You would normally define a time step, delta t, which is the t final you've chosen, which in our case is tn, minus t initial. And this is divided by n. So this is in our case tn minus t0 divided by n here. You've probably seen this many, many times. And the solution is typically given by x of I plus 1, which is the same as x of t of I plus this time step delta t. I hope you don't get offended if I remind you of some of the basics of differential equations. And this is now given by x of I, so that is x of I at the time ti, plus the derivatives multiplied with some delta t times something which I'm going to call a ordinary differential equation integrator. So this could be, in the simplest case, it could be Euler's method, Euler's feed-forward method, which essentially just contains the first derivative, which is this function f, which we've chosen. So if we have Euler's method, then what we would have then is f of x of I, of t of I, which is then included here. If you have a Runge-Kutta family of solvers, then this would contain integrals over the different approximations in the Runge-Kutta solver. If you're using an Euler-Kromer method, you have different ways of dealing with the updates. If you're dealing with energy conserving models, like the velocity-Valère differential equation solver, then you would have a solver both for velocity and positions, and this would feed into each other. So we are just leaving that out. So what we have then is an x of I plus I, which is given by x of I plus some delta t multiplied with this ordinary differential equation integrator, ODInt. So I'm just writing this in a very generic way without specifying it. And that typically depends on x of I and t of I. It could also depend on derivatives. Okay, so this means that we are now going to define for the neural network. So for the NN part, for the neural network, in order to make predictions, we're going now to train a network so that this x of I defines the input, and x of I plus 1 defines the output. So that will be the targets, as we have been labeling them, which then define the objects which we want to reproduce. So that means that at every time step, we are going now to produce data, x of I plus 1, x of I plus 2, up to the final time. And these are going to serve alternatively as inputs and outputs to the neural network. So you would typically train with an x0. So you could think of starting x0 is the first input. And then you would have x1, which would then be the first output. And then this just gets repeated. So you would have x1 equal to the second input. And then you would have x2, which is the second output. And so you would continue like this till the final one, where you would have xn minus 1, and then xn as final input. And this will be the final output to the model. And then we would train a neural network, and we could split this data, which we now have produced by the differential equation solver. So the differential equation solver, which we have chosen, this ordinary differential equation integrator, that is going to produce these solutions for us, which we then use to train a neural network. So what we are going to do then is just to feed this data in, and then we will have some of the data as test data and some of the data as training data. And then we see how well the neural network predicts our results. So that was more to give you the kind of overarching view of what this project is about, or this specific path is about. So let me just go back to the Jupyter Notebook then. And in the Jupyter Notebook, what you will find then is a skeleton of a program, which now takes as input these data sets which we have produced. So you will see now I have a delta t, which is 10 to the minus 2, a final time. And then I simply arrange an array with the times. And then I define an input. So what I'm going to do now is to solve these differential equations for many types of initial values. So remember now that when you're solving a differential equation, you have to specify initial values. So what I'm doing now is just to specify these initial values randomly. And I just select 100. So that means that I have an array with 100 initial values for the three dimensions x, y, and z. So this 3 here and 100 defines a matrix of dimensionality 100 times 3 of input values. And each input value is going to give us a different solution. So I'm putting up the derivative of which are just actually these equations which you see here. These are the derivatives I'm punching in. So this function Lorentz derivative, that simply returns the values of the derivatives given the sigma, beta, and rho parameters. And you can see here it returns x minus y times sigma. And this is the dy dt term. And this is the dc dt term. And then I generate 100 random initial values. And here you can actually plug in your own differential equation solver. You could make it as simple as using Euler's method, which still works. And then you would simply then call the ODInt solver, which follows SciPy, and then simply define the derivatives. And this sets up the solution for us. This array x of t given an input. And then what I'm doing now is, since I have 100 initial random values, then I'm going to have a set with 100 initial values, which define my inputs. And I'm simply setting up an array, and this would be xt, and this is now the xt plus 1, so that's the output. So what I'm setting up here is the input and the output for training a neural network. And the input and output variables are those that we will start trying our network with. And the first task here is actually to set up a neural network code, and you can decide whether you want to use your own code or you want to use the functionality of, let's say, PyTorch or TensorFlow. And in order to do that, you can look back at the codes and the discussions we had earlier. And then you will simply set up the runs with a neural network and see how well the neural network is doing. When doing this test, you should just pick 1 or 2 initial values and just see how the solutions develop. Now, if you don't like that, you can replace that with a standard Runge-Kutta solver, which I put up here, which simply looks at the harmonic oscillator. And in that case, I have a spring force acting on a block, a very exciting system, a block which slides back and forth in 1 dimension. And it has a damping term given by this parameter gamma times the velocity. So it doesn't move that fast. So we assume that friction is given by a linear term in velocity times a damping factor gamma. There is an external force, F tilde, which is a cosine modulated by the frequency. And then I have the X value, which comes from the standard harmonic oscillator potential, and which gives us a force which goes like minus a parameter K times X. And here's a Runge-Kutta solver to 4-folder for this specific case. And I'm solving for the velocities and the positions. So the final position and velocities are given here as a weighted sum of these different contributions. And there are 4 in total, which defines the Runge-Kutta to 4-folder method. And then you see the main part here is a part where you set up the initial arrays for V and X and time. It's a 1-dimensional problem. I have an initial condition, which you can change to more than 1 dimension if you find that boring, just to be in 1 dimension. And you can also change it to be random. So you could mimic the previous case, which we have for the Lorentz attractor. And this system here now produces the output, and the output is plotted here, as you can see. And this will be your data. And again, you would now take the X values as a function of time here, and you would simply now use the one value as input, the other value as output, and then you would continue so that you have a set of input and output values, which you then would use to train a neural network. So that's one possibility. The next step, if you want to do that, is actually to use a recurrent neural network, which is often one of these deep learning methods which are tailored to solve time series, because what you're having now is a time series. And we are going to use this example, which you see here now, to also present the mathematics and the layout of a recurrent neural network. So I'm trying to, adapt the discussions of many of these deep learning methods to problems from the physical sciences, in particular solutions of differential equations. Now, what I also have added here is a partial differential equation path. And for this variant, you can actually use these lectures, which we also have from week 6 and 7, where you can find additional material on how to solve differential equations. And this will be you solving the standard diffusion equation. If you want, you can replace that one with something which is more relevant for your research. And I know that some of you may more be interested in, let's say, solving the Navier-Stokes equations in fluid mechanics. and there's a lot of research on solving Navier-Stokes equations and similar equations using neural networks. So what I'm suggesting here is just a possible implementation of it. You don't need to follow my suggestions. If you have something which is closer to your research, I mean, feel free to do that. And what follows down here is just you first solving the differential equations using standard methods, like an implicit method and an explicit method, if you're familiar with that. And then the final part is actually to use a neural network and then compare the solutions with traditional methods and neural networks. So that's another possible path. So any questions so far? So let me just stop sharing here and let me hear if you have any comments, ideas, thoughts about these projects. Or I shouldn't say projects, but I should rather call them different research paths. So again, feel free to adapt what I'm suggesting to your own research. It seems a total silence here. I hope this was not too intimidating.
You want to say something?
Yeah.
No, I don't think we have nothing to say.
We are fine for the moment with second project.
Yeah, just give it a thought and see if what I have designed. So I've tried to collect, how to say, the kind of inputs you gave me about your own research and find something which perhaps overlaps more with what many of you may be doing. But I may have missed it totally, actually. So feel free to, especially in this project too here, is a project where I think you should, if you have ideas you want to follow up with deep learning methods, and if that is relevant for your PhD project, please do try to see if there are possibilities to change and adapt these to your own research.
Morten?
Yeah.
The project 3 will be on the same way. I mean, because for example, this one is perfect for my research.
Yeah.
But I saw that the third one is about Bayesian inference and that kind of methods. So it would be the same way.
Yeah.
The third project will be about Bayesian methods, right? And
so one thing we did last year is that last year we had a group of 3 people who were more interested in solutions of partial differential equations. So what we did then was to say that, okay, for project number 3, what you do is actually you extend the project number 2 and you go deeper into your own research. So that means you don't do the Bayesian project, but you follow up with what you have done. And if there is a possibility to overlap, actually, if you think of some of these kernel methods and also Bayesian ridge regression and so on, that has actually been used in solutions and studies of differential equations, for instance. So there is a possibility to sneak that in. Alternatively, you can take this project number 2 and say, I would rather like to define a project 3 or an extended project 2, which follows my own research path. And we did that with people last year because there were people looking at the solutions and the Navier-Stokes equations. And they wanted to go more in depth with the solution of differential equations. Also because that group consisted of people who hadn't studied the normal way of solving differential equations as well. So you have lots of methods for solving partial differential equations, the so-called standard methods, like finite difference and finite element methods. So they actually wanted to follow that research path, which was more adapted to their own research topics. So we want you guys to have this kind of, we are just defining some kind of possible paths. And then clearly the thing which is interesting for many of you is to try to adapt this to your own research, if it's possible. Any other thoughts, ideas, things which come to your mind before we move on to one of the more popular deep learning methods, which is convolutional neural networks? So just give it a thought and see how things align with your research. And keep always in mind that we want you to have this kind of flexibility that you can adapt the projects to your research. Okay, I hope it's not too confusing. Then I have this bad tendency of giving too many options to people. But I think that's what makes it a little bit more interesting. And it makes it more interesting for me to teach as well, because I learn a lot when I read your projects. So there's a win-win probably for all of us. Okay, so there don't seem to be any questions. So what I would like to do now is to start looking at convolutional neural networks. So what I want to give you first, before we take a break, is actually some general information about convolutional neural networks. And if you now think back to what we have done with neural networks, in neural networks, we have what is called a full connectivity. That means that every node in a previous layer is connected with every node in the next layer, whether this is the input layer connecting to the first hidden layer, or just one hidden layer to another one, or the final output layer connected to the previous hidden layer. So that means that the matrices with the unknown parameters, the weights and the biases, they are dense matrices, and we perform matrix multiplications and matrix vector multiplications with dense matrices. So clearly then this becomes a problem when we have many parameters which quickly exceeds the available dimensionalities which we can deal with. So CNNs, and this is something which I want you to keep in mind now, they contain many of the same elements as a standard neural network with a backpropagation. There are typically so-called dense neural network parts in it, but there is also a filtering which is given by the mathematical process of convolution. So convolution is a way to filter and reduce the dimensionality of your data. So that means that convolutional neural networks are networks which you have to think of as hand-tailored networks to specific problems. So if your problem is to identify houses, clearly you have images of houses, you would not keep details about the painting of the house. I mean, the walls have the same painting, and you could just keep some few details. So if you have a picture which consists of 200 times 200 pixels, and it has 3 color channels, the standard color channels, this is a picture which has a dimensionality of 200 times 200 times 3. And clearly, if you have many such images, millions of such images, this becomes a huge problem to train. So when you now take this picture of a house, you would then hand tailor it so that you don't keep all the information about the walls, because the walls may have the same color, but you would keep the information about the corners, the roof, where it begins, where it ends, windows, doors, and similar things. So the convolutional neural networks are actually a way to reduce the dimensionality of the whole problem. So think of many of these methods in an overarching way as dimensionality reduction method. And much of this is based on the mathematics of and computer science methods for filtering and image recognition. So till the advent of convolutional neural networks, a method based on principal component analysis and singular value decomposition, which we discussed in the beginning of the fall semester, they have been very popular methods. However, since we are dealing with matrices, then the dimensionality can quickly become very, very large. Convolutional neural networks have actually, perhaps we could say, they defined the set of methods which really made deep learning methods popular. Because when it comes to classification of images, they have had an enormous success. And it is the method of choice in classification algorithms of images. And if you're thinking of algorithms for face recognition, then convolutional neural networks are actually the basic, they form the basic methods, or the basic approach to that. And you have data sets like ImageNet, which is a huge collection of images, which has been pre-trained on specific types of images. It could be images of cats in different modes, cats sleeping, cats moving, cats in different backgrounds. It could be other types of animals, which you then could train with millions and millions of images. And then you have a pre-trained network, and then you can feed in a new image and see if that network is able to recognize what kind of image this is. This pre-training is also a very important thing if you're doing physics analysis. So in many cases, when you run, let's say, a physics experiment, just to give you an example, and you produce images from, let's say, a detector. So you could have the path of charged particles in a detector, and they will typically bend according to the strength of the magnetic field. And they produce paths in the detectors. So you detect the positions. The detector typically has a specific depth, and you can produce images then which tells you that this could have been a proton decay, this could have been an alpha particle which was emitted, and so on. They will all have different paths, and you could train theoretical models to pre-train a network, and then based on your experimental data, which now are images converted from the results you have observed in the detectors, then you can use these images and then figure out whether this was a proton decay or it was another type of decay, which you have pre-trained in, let's say, from a theoretical simulation. So that's just one way of thinking of what is coming now. So if you think of neural networks, these are normally called affine transformation. That is typically a vector with input is received and is multiplied with a matrix of so-called weights. And they define or unknown parameters, and that produces an output. And we, in the setup of a standard neural network, we actually do this again and again and again. And these are dense operations. So when you deal with images, on the other hand, you have important properties of the images which we can focus on in the training. So CNNs, just to keep that in mind, CNNs are actually ways of recognizing images where you have, in a way, tailored the type of images, the algorithms to the type of images you want to look at. So the filtering which you're going to do is going then to reflect the type of images you want to classify. So that could be, for instance, the width and the height axis for an image. It could be a time axis for a sound clip. And one axis, which is normally called the channel axis, is used to access different views of the data. It could be the red, green, and blue channels of a color image, or the left and right channels of a stereo audio track. And these properties, when you feed them in a standard neural network, they are never exploited. And actually, all the axes and all the inputs are treated in the same way. And the topological information which you have is not taken into account. So taking advantage of this kind of structure of the data may be difficult in solving some specific tasks. And this is actually where there's a lot of research being put into specific types of tasks. So a discrete convolution, as we will see, is a linear transformation that preserves the ordering. It is sparse. That means only a few units contribute a given output unit, and it reuses parameters. So I see my time, we've just passed the hour now. So I would suggest that we take a small break, and then we use the next lecture to look more at the mathematics of convolution, and then look at how we can implement the mathematics of convolution in this specific filtering. So keep in mind, this is a way to reduce the dimensionality of the problem, but at the same time, it involves a lot of hand tailoring to a specific problem. And that is where the success of convolutional neural networks actually lie. So welcome back. And what I wanted to do now is more to give you first a kind of basic overarching view of a convolutional neural network and why we would like to use them compared with standard neural networks. And you will quickly see that if you have an image, let's say you have something like 32 times 32 pixels, and then you have 3 color channels. So it's a typical an image which is 32 wide, 32 high, and 3 color channels. So it's a 3-dimensional object. And if you think of this connecting to the hidden layer, you would then have something like 3072 weights. If you, however, want an image with higher resolution, let's say 200 times 200, just this image leads to 120,000 weights. And that's becomes a matrix which is very, very large. And the amount of weights you need to train starts quickly growing. And if you in addition add more and more images, suppose you have 1 million images, and you have for each of these images you have 120,000 weights, you can easily do the mathematics and see that the dimensionality becomes unwieldy quickly soon, pretty soon. So the thing now is to actually try to reduce the dimensionality of the image by some kind of filtering. So if you think back of this image, 32 times 32 times 3, the idea now is to take the full image, which would be this box you see here, where you have my arrow, and to reduce it. And then there are different filtering processes. So this image here may now consist of several filtered images. And then you can pre-process it again through some new filtering process. And then at the end, you end up with some data which you could feed into a standard feed-forward neural network. So we are going to look in more details on how these processes can actually be achieved. So typically in a neural network, which is converted into a convolutional neural networks, there are specific layers or specific elements of the CNN architecture. And these are typically layers of the type of the input layer, which will be the same, irrespective of whether we do a convolutional neural network or a standard feed-forward one. There is a convolutional layer where we can actually reduce the dimensionality. We can apply many different filters. And these different filters, which reduce the dimensionality of the image, they can now represent different parts of the image. And then based on that one, so this convolutional layer produces either one or many more filtered versions of the image. So the convolutional part is the one element of the dimensionality reduction. And then there is a ReLU layer, which actually produce an output via an activation function. And typically, this could be the ReLU function, and it's often the one which is implemented in convolutional neural networks. And so it's just called a ReLU layer. And then there's something which is called a pooling layer that performs a further downsampling of the data set which we have. So this pooling is a further dimensionality reduction process. So you have a so-called convolutional layer, which now perform where you have the filtering. But normally this convolution plus ReLU plus the pooling is seen as a kind of common, these are common elements in the total convolutional layer. And then we have a fully connected, so which then we could treat this as a standard feed-forward neural network, where we perform the standard training as we've done before, but with a downsized scale of the image. So these are the typical steps which we are going to look at. We're also going to look at the type of hyperparameters which we are going to implement in connection with the setup of a convolutional neural network. So CNNs in brief, that's the simplest case. In the simplest case, it's a list of layers that transform the image volume into an output volume. And there are a few distinct types of layers. This is a convolutional layer. There is the fully connected layer. There's a ReLU part. There's a pooling part. These are the most popular ones. And each layer may or may not have parameters. So the convolutional part has parameters, which you need to train. The fully connected one has. The ReLU and the pooling layer do not have, except that they have hyperparameters. But these hyperparameters are fixed before we run the calculation. So the training is typically done in the convolutional part and the feed-forward part, or the fully connected one. And there we encounter again the backpropagation algorithm. And these layers may have different hyperparameters, and this ReLU layer typically does not. And the convolutional, the feed-forward, and the pooling part may have hyperparameters, which come in addition. And we are going to encounter all these kind of details which enter the setup of a convolutional neural network. So if you wish to read more, I mean, the textbook by Goodfellow et al. Is actually the one which contains a lot of these technicalities about setting up a convolutional neural network. So what I wanted to do now is to give you the basic ideas of what convolution is. So to look at the mathematics of convolution. And if we just keep in mind that the dense neural network is something which is represented by an affine operation like matrix-matrix multiplication, where all the parameters are included. And the key idea in a CNN is that in images, neighbor pixels tend to be related. So just think of the colors or the color of the walls of a house. I mean, there is no point in keeping the information if you have just a picture of a wall with one or two windows. There is no reason for you to keep the information about all the pixels which represents the same color, just to give you an example. So the filtering is given by the mathematical operation of convolution. So I'm going to abuse a little bit with slides today, because I just wanted to go through some examples. And one example which many of you have encountered of convolution is probably in connection with the Fourier analysis. But I wanted to give you a simpler case first. So mathematically, convolution is defined if you look at this one-dimensional example. So you could think of some continuous function y of t, and you have some data, x, which now could represent your input data. So suppose you measure this x, you measure the position of a car as a function of time. So a is time here. And this is a full measurement. This measurement could be noisy in the sense that you can have measurements you made where the position of the car is less well determined. And then you have other measurements where it's more determined, well determined. Now, one way to often deal with the noisy part of the data is to filter it away in some way or the other. And that process represents the process of convolution. And this weight function W is normally called a weight function. And this above integral, which you see here, is often written now in terms of this x, and then you have the asterisk signs with W, and as a function of time here. So that this mathematical representation here represents actually this integral. So what we are doing now is, suppose now that up to a time t, our measurement was pretty crappy. And that means that we want to filter away some of these measurements. So we are giving a weight from a time t minus a, and then we weight the input with this specific function. So that's a specific filter, which we are setting up. So we can now set up a discretized version where now, and this is often the more actual case which we encounter. Typically, if you have an image, the image consists of pixels, so it's a discretized set of informations which we have. And then we could filter our image, and this is multiplied with the input image, the raw data, and that produces an output here which is now filtered. And we keep the information about some specific points in this image which we have, or this data set. So computing the inverse, and you may have seen some of the mathematics here in connection with Fourier series and convolution defined with Fourier analysis. Or if you think of a Laplace transform, that's another example of a convolution. And the process is actually the inverse process, leads to what's normally called deconvolution. So the question is, how can we use this? That's actually the question for us. I mean, how do we use the mathematical process of convolution in order to produce a filter or to perform operations here? So if you now think back to project 1, where we tried to set up a design matrix for two-dimensional function, this Franke function, which some of you studied, that was an example of a polynomial multiplication. Now, I can actually rewrite a polynomial multiplication as a convolution process. So suppose now that I have a second-order polynomial, which is this p, which depends on this variable t, and I have another polynomial, which is a third-order polynomial. Now, when you perform a polynomial multiplication, you don't do the brute force calculations, because that would be a waste of floating point operations. There are actually smarter ways of doing the polynomial multiplication, and convolution offers one of these. So if you now think of the final outcome here, the final outcome should be a delta 0, which obviously is alpha 0 times beta 0. There should be a delta 1, which collects the terms with the t. So that will obviously involve alpha 0 times beta 1 and alpha 1 times beta 0. And then we have delta 2, which goes like t squared, and up to delta 5, which involves a fifth order term, which comes from alpha 2 times beta 3. So that's a general structure. So if you think of the multiplications here, oh, by the way, I see I've forgotten to fix this typo. This should be alpha 1 plus beta 0 plus delta 1 times alpha, no, beta 1 times alpha 0. So this is actually a stupid copy and paste, as you can see. So this should be alpha 0 times beta 1. So let me take note of that one and try to fix it right after the lecture here. Then the next terms would be linear combinations of these different coefficients. So if you look at the equation we had here, they contain now these different coefficients. And alpha I is 0 except for these values of I, and beta I is 0 except for I when it's 0, 1, 2, and 3, by obvious reasons. Now you can obviously rewrite this in a less elegant way, but this is actually the convolution which we have here. If you think of back here to the discretized version, where a goes from minus infinity to plus infinity, we could now let the parameter I here go from minus infinity to plus infinity, but we could have had tests, because I, when I is different from 0 to 3, then this produces just zeros. So we could actually sum from I equals 0 up to I equal to 3. Actually, in this case, it suffices to do that. And this is now simply the convolution process, which represents this multiplication. You could alternatively rewrite it as a double sum like this. That's another possibility, where L is I plus j, and then you run freely from I, j by putting the constraints which you have here for where the polynomial is defined to be different from 0. So these equations here, if we just sum freely, clearly this is not the most efficient way of doing it. So we would typically put in these summation constraints, which we have. So you could also think of encoding this in terms of matrices times vectors. And one way to do that is to define this matrix here. And you can see now that you have along one of the diagonals or subdiagonals, you have the same value. So you have an alpha 0, which gets repeated here, an alpha 1, which gets repeated, and an alpha 2, which gets repeated. Alternatively, since now the process is commutative, you can rewrite it like this. And this is actually going to use less floating point operations because this is a matrix which is dimensionality 6 times 4, and this is a vector of length 4. Whereas here we have a matrix which has dimension 6 times 3 and a vector of length 3. So that gives actually less floating point operations. Now, a matrix like this one has a special name in the literature where you have this kind of constants, the same values along one subdiagonal or the diagonal. Does any one of you remember what kind of name these matrices have? These are famous matrices in linear algebra, which you encounter in many, many applications, actually. Anyone remembers what these matrices are called? Where you have this kind of constant along one of the subdiagonals or diagonal? So this, I'm just going to put it in the chat here. So the matrix which you see here is actually called a Toeplitz matrix. Now, the reason why I'm bringing this up is that when we now are going to look at the process of convolution, we are going to actually rewrite the filter, the way we do the filtering in terms of a Toeplitz matrix times an input vector, or vice versa. We rewrite the input vector as a matrix, and then we have a vector which represents the filter parameters. So just keep this model which you see here in mind, because we are going to look at a modified Toeplitz matrix, which is actually called a circular Toeplitz matrix. And we are going to rewrite everything in terms of efficient matrix vector multiplications, where we have Toeplitz matrices, which are normally sparse matrices. So you can see here, if you were to increase the structure of this problem, you would have many zeros here. And that's something which then defines a sparse matrix. And this matrix vector multiplication can actually be performed in very efficient ways. So the basic mathematics, which is implemented in the filtering or the convolution stage, is a rewrite of the data in terms of a Toeplitz matrix and a vector, which then could, let's say, represent the input data. And we are going to look at examples of that pretty soon here. Any questions so far? So this is just to give you a kind of anticipations of what is coming. So when you look at the convolution itself, there's perhaps another way of looking at convolution which you have seen before, and that is the superposition of periodic forces through Fourier transforms. And if you think of a problem like the one which I mentioned as an alternative data set for solving differential equations, you could now think of this type of differential equation then, which where you have this f of t could be an external force which is being applied to the system. And this external force then could be a sum of many driving forces. And these forces are normally periodic. And these periodic forces are forces which we then can represent by a Fourier expansion. That means also that we can find, let's say, the particular solution in terms of Fourier expansions. And you know that if you look at the Fourier's theorem, Parsifal's theorem, and all these elements of Fourier analysis, the principle of superposition plays a very important role. And we can actually expand the periodic functions in terms of sines and cosines. So that means that if we have a function like this f of t, which repeats itself with a period tau, then this is something which is almost ideal for a Fourier analysis. And typically the problem which we put up here is also a problem which, if we take away this force, can be modeled in terms of exponentials, the solutions of it in terms of exponentials, and thereby cosines and sines and periodic functions. So this is a problem which almost begs for a Fourier analysis. And if you remember from Fourier analysis, this is a field of mathematics which is extremely useful, and it allows us also to solve partial differential equations. And we can rewrite the partial differential equations through a Fourier transform in terms of an ordinary differential equation in just one of the parameters. And that's also extremely useful. So if you look at the principle of superposition here, here's a simple Python code, which I put up here. So suppose you have this function here. This is a data set you produce. So you have a square signal. This is actually a signal which you can reproduce with a Fourier transform or Fourier expansion. So you can actually replace this one in terms of a constant term plus a set of cosines and sines, and where you can actually find these different Fourier coefficients by using the orthogonality of the cosine and sine functions. So what you have here is just a quick wrap-up of some of the basic ways by which you find the coefficients. And I guess most of you have seen this before, and you can actually calculate these coefficients here. So if you look at the that specific function here, what I'm doing now is I'm setting up 500 data points. I have an initial time and a final time for this periodic pulse. And I let the periodic pulse have a period of 0.2. And I look at the max value of the square signal. So I'm just setting up some parameters and the width of the signal. And then I can actually parameterize this function in terms of a sine and cosines. So this is my Fourier expansion, which I'm setting up here. And if you look at that one, you see now that with that approximation, so the orange lines here, this is actually my Fourier expansion, which now reproduces this periodic signal, which was in the original data set. It was just given by this square or this square signal here, which repeats itself. So you see the power of Fourier transforms, which now allows you to actually reproduce this data set in terms of a set of cosines and sines. And this is extremely useful in case you have periodic functions. So like that example which I put up, the periodic or the problem with a sliding block for project number 2, this is a problem which we can obviously solve by using Fourier analysis. Now, what I wanted to do before we move on to the setup of a convolutional neural network, I just wanted to remind you quickly about the convolution with a Fourier transform. So let me just switch back to the whiteboard. So instead of putting you to sleep with slides continuously, what I'm going to do now is just to remind you quickly of a Fourier transform and convolution, in case you may have forgotten that. So that would be our example 2 here. So let me just put this up. So convolution and Fourier transforms, or Fourier theory. And Fourier expansions or series. So if you think now of the process of convolution, so what we have defined, if we now think of this in terms of a continuous functions, we have a g, and this has an argument x, and this is now given by an integral from minus infinity to plus infinity, and we have some f. This is our filter, x, and then we have some original function, which depends on this parameter. So this is the basic definition of the process of convolution here. So what we could think of now is that we have a function now, f hat, which is a Fourier transform of an original function, f. So this uppercase letter f here is actually the Fourier transform of the function f. And similarly, we have a function g hat, which is given by the Fourier transform of a function g. So if I now take the inverse Fourier transform of f times g, so if I take f minus, and then I have my f hat times g hat with an argument x here, that is going to be given by 1/2, and then I have divided by pi. I'm just putting in the definition of the Fourier transform. So I have an e to an I over omega x, and then I have my functions f hat as a function of omega and g hat as a function of omega, and this has d omega as integration variable. So this is a formal definition which you would typically find in every textbook here. This is something you can rewrite as minus infinity to plus infinity of this f hat of omega multiplied by e of I x, and this is again given by the Fourier transform of this function g hat. So g hat and f hat, they are just a Fourier transform of an original function. So I could now plug in the Fourier transform minus infinity to plus infinity, and then I have my g of y, and then e to the minus I omega y, and then I have a d of y, and this is multiplied with the original d omega. Now, if you look at the definitions which we have here, if we now put this f hat omega and e I omega x inside the inner integration, what we have then is a 1 over 2 pi minus infinity to plus infinity, and then we have an integral from minus infinity to plus infinity, and then we have our g of y. So this is nothing. The g of y here is the function which we are Fourier transforming. So we have f of w as a function of w of e to I of omega of x minus y, and this is multiplied with dw and multiplied with d of y here. So this is just a plain rewrite of the same functions which we have. And if we now repeat this exercise, what we get then is minus infinity to infinity of g of y, and then we have an integral over 1 of 2 pi minus infinity to plus infinity, and then I have an f of y of e of I of omega of x minus y multiplied with dw, and this is then multiplied with d of y. And the function which you see here, this, let me just bring more space here. So this is multiplied with d of y. So this function here is nothing but the Fourier transform of f of x minus y. So that we end up with then is actually the process of convolution here of g of y multiplied with f of x minus y of d of y. And this is the same as what we wrote earlier as g convoluted with f, which is also the same as f convoluted with g, because the process is commutative. So this is something you may have seen before, and it's just another example of the mathematical process of convolution with Fourier series and Fourier transforms. Now, this was a kind of mathematical background for what is going to come now. So what we need to look at now is actually the, let me just bring back the slides just for a quick moment. So what we're going to look at is the convolution, which we are going to implement when we perform this filtering of a data set. So you can now think of a filter which is defined by a kernel, K. So we get an output where we have this input, which now contains our image with all the different pixels and color channels, etc. And this is then filtered with this K, and that produces a final output. And that could be the image, which we then would transfer to this kind of ReLU layer. And then we have this pooling layer where we additionally transform or reduce the dimensionality of the image. And that could be fed in finally to a standard feed-forward or a fully connected network where all the nodes are connected from one layer to another layer. So normally what you would do is actually to implement, since this is a commutative process. I see there are some typos here, commutative process. Yeah, I have to correct that one. So sorry for that. There are some typos I need to correct after the lecture. And normally what is implemented is actually this one. So in a typical machine learning library, since there's less variation in the range of the values of M and N. In many libraries, they implement something which is called a cross-correlation instead of a convolution. And in the cross-correlation, there's a typo here as well. It should actually be J plus N. And this term here is easier to implement from the number of floating point operations, but it's still referred as convolution here. So just to give you a final example before we dive back into the whiteboard. So if you think of in a field like signal processing and imaging as well, we now have to define these filters. And the way they're implemented is through the process of convolution. And think of a data set where you have an input vector of length 10 to the 6. Then you can construct a standard feed-forward neural network with only one hidden layer with 10 to the 4th nodes. So that means that you have a weight matrix with 10 to the 10th weights to be determined, together with 10 to the 4th biases. So that means that the number of parameters you end up with is roughly 10 to the 10th. And this is a huge dimensionality. So in today's neural networks, you can actually train such networks. However, there's a huge number of parameters for the task at hand. And in general, it's very wasteful and inefficient to use these kind of dense matrices as parameters. And such trained networks are often very specific for the type of input data on which they were trained. And the network is not likely to generalize easily to variations in the input. And the main principles that justify convolution is locality of information and repetition of patterns within the signal. And typically sound examples of the input in different spots are much more likely to affect each other than those that are very far from each other. And similarly, you would find that sounds are repeated in multiple times in the signals, while slightly simplistic reasoning about such as sound examples demonstrates this. The same principle then applied to images and other similar data. So what we are going to do now is actually to go and look more into how we would encode a convolutional neural network. So let's go back to the slides, not to the, sorry, to the whiteboard. So let's set up some of the first elements, and then we will try to wrap this up next week. And let's just call this basics over CNN. So the first part is the filtering or the process of convolution. Now, when you set up a neural network or a CNN, you can actually have many such filters, and you can produce from the original image you can produce many downsized images, and then you can feed this forward to a new convolutional layer, where you then produce another set of filtering, and you can actually continue like this till you have a downsized image or sets of images, which you then feed into a standard feed-forward neural network. But let's now look at the process itself, and let's set up some of the basic mathematical operations here. So suppose I have an input matrix which contains some data sets here. So input is now given by a 3 times 4 matrix. And then I'm going to have a filter here, which is now just a 2 by 2 matrix. So I'm going to use this example here to also introduce some specific hyperparameters, which are called stride and padding. And you will see from the implementation of convolution here what stride means and what this padding also means. So let's now assume that this input, which is now given by this 3 by 4 matrix, looks like as follows. So it's going to be an exciting example. So I'm just testing out my knowledge of the alphabet. So A, B, C, D, E, F, G, H, I, J, K, and L. Sometimes I used to pull people's legs and just writing wrongly some of the letters here. And then we have a filter which looks like this. So there is some value W, there's some value X, there's some value Y, there's a value Z here. So what we're going to do now is to perform the filtering on sizes of this matrix. So we're going now to pick the first block here. So we're going to downsize this filter, and we're going to downsize it to a 2 by 3 matrix. So this is going to give us a 2 by 3 matrix when we have downsized it. So you could think of this as using convolution to downsize the size of the input. So what we get then, so let's just bring this up again, since we use this red coloring. There's going to be a slot now, where I now multiply the different elements. So I'm going to have A times W plus B times X plus E times Y plus finally F times Z here. So that's my first convolutional result. So I'm just simply applying the formula which we put in the slides. My next layer, and now I'm going to use what's called stride equal to 1. So I'm just going to move 1 unit here. So stride equal to 1 means I just move 1 unit in doing the convolution here. So that means I'm going to get a new layer, a new element in this 2 by 3 matrix. So this is going to include now B times W plus C times X plus F times Y plus G times Z. So since I have a stride equal to 1, it means I can now move 1 further step here. So this is this one. So I get the next step. And this is going to be C times W plus D times X plus G times Y plus H times Z. Now, since I have stride equal to 1, it means that if I want to move further here, I'm actually getting out here, and there is nothing. So that concludes my operations with the first 2 rows. Then clearly, I can go stride 1 down. So that means I can go down here, and then I can single out this block. And it means I will also have this block later. And finally, I'm going to have this block. So it will be 3 more blocks if I now just implement my convolution straightforwardly. So let's change color here. So now we are going to have a green one. So this is going to be my green block here. So hopefully you can see the colors well. So my green block is going to be E times W plus F times X plus I times Y plus J times Z. And then I have two more blocks. So let's just bring that up. So the next block is going to be this one. And then I have my F times G plus F times W, X times G plus J times Y plus K times Z. And then I'm just going to put up the final one. And this is probably as far as we get today. So my final one is now going to be given by this color here. So this is my final block. And in this case, I have G times W plus H times X plus Y times K plus L times Z. And this has now produced a 2x3 matrix. So one thing which you note now, when I put this stride equal to 1, we could obviously have defined another stride. So we could have had a stride of 2, but that would have given us, if we take a stride of 2, that means that I would do this block, and then I would do that block. And finally, I would not have a block with stride 2 down here. So that would not actually be possible to do. So stride equal 1 is the only stride which I can have for this specific example. Now, there's one thing I wanted you to note now. And when we perform this convolution here, if you think of the information which we transfer through the filter, so this is our filter. If you look at the corners of the matrix which we have here, A, D, E, and I, you see now that the information about A appears only here, whereas B is here and here. So it's in two other slots. If you look at the other information, if you look at a quantity like C, that appears also in two other slots. If I, however, take the variable D here, you will see that D appears only here. And the same applies to a quantity like E. So all the corners, all the values along the edges here, they actually appear only once. This is something which can be compensated by adding an additional layer outside with only 0 values. And this is called padding. So you can make padding of a given size. So this padding and stride, they introduce hyperparameters in your filtering, so which you need to play around with. So the way you set up your filter and the way you perform the operations here depends on the way you define the stride, and also the way you look at the data being transferred to the reduced matrix or your filtered image, if you want to look at images. This is something which now can be improved upon by adding a specific padding around the data set which you have, which you just fill in with zeros. And then what you will see is that a number or a data set like this represented by A appears in more than just one slot. So we are going to look at these these technicalities in further detail next week. And then we are going to set up as well how we can use Keras to construct a convolutional neural network. But I just wanted to go through some of these basics because convolution is the way by which we do the filtering. And next week, we will discuss more the different hyperparameters and how we can further reduce the dimensionality of the problem by performing additional filterings of the images. But this stops today's lecture. Feel free to take a look at the project and see if it fits with your research interests and your interests in general. And just give me feedback on the projects and whether you have alternative ideas and so on and so on.